Hello, my name is Kimberly Karras, and today we're going to discuss a problem in the textbook Matter and Interactions, Volume 2. This is Chapter 14, question number 48. In this question, we have to place a helium nucleus and a proton, and eventually in the second part an electron, in such a way that the net electric field due to both of these charges is 0 at an observation location marked with an X. We know that the distance is between the helium nucleus and the observation location is 1 times 10 to the minus 10 meters. So in order to do this problem, we have to first know that the electric field of a positively charged particle points outwards, like this picture right here. And in the case of the proton and the helium nucleus, both of those are positively charged. So their electric field should look something like this picture. So the first step in solving this problem is we have to draw what we know. We know we have a helium nucleus which has 2 protons and 2 neutrons, is 1 times 10 to the minus 10 meters away from some X. I went ahead and drew the electric field due to the helium, which points to the right because this is a positively charged particle, so it's going to point to the left. It's going to point outwards. So if we have to find an electric field that points to the left, which is the opposite direction but equal in magnitude of the electric field of the helium, and our charge must also be positive, we know that the positive proton must be somewhere around here so that it can have an outward electric field to the left. So a proton has to be somewhere around here, which is like in this picture, right here. The proton's this way, and it's going to have an electric field that points somewhere to the left. But we want to have this electric field from the proton to be equal in magnitude but opposite in direction of the electric field due to the helium nucleus. So we need to find out what distance will make this the case. So we know that the general location of the proton, which is somewhere around here, but we need to do calculations to actually figure out what this question mark distance is. We have to make use of the equation of the electric field of a point charge, which is 1 over 4 pi epsilon naught times q over r squared times r hat, where r is a position vector from the source to the observation location. So what we're going to do first is we're going to find the electric field due to the helium nucleus, because we know everything for that. So to get r, we do observation location minus source, and I just happen to set the origin of this system at the observation location, so the observation location at 0, 0, 0. The helium nucleus is on the negative x-axis, and the positive proton is on the positive x-axis. It's some distance z. I just called it z. So basically what we do is we plug and chug the information that we know from the distance and the charge of the helium nucleus, which is 2 times 1.6 times 10 to the minus 19 coulombs, because there are 2 protons in a helium nucleus. So after we plug and chug into the formula, we get this to be our electric field due to the helium nucleus. The next step is we have to find the electric field due to the proton, and we use the same exact equation but use our z point for our source, and we plug and chug into the equation, and we have to solve for z in the end. So we have to set E net is equal to the electric field due to the helium nucleus and the plus the electric field due to the proton, which means that the electric field due to the helium nucleus has to equal the negative of the electric field due to the proton. So what we do is we did exactly that. We set both equal to each other, and we broke the electric field into components, considering that the y and z direction are both 0 in our system. we can just not really think about those too much and just focus on the x direction when we set them equal to each other. We solve for z, and we end up getting this distance for z. We get 7.07 times 10 to the minus 11 meters, which is how far that this proton should be away from this observation location, such that the net electric field at the x is 0. And the next part of the question is we had to do the same thing, except instead of a proton, we have an electron. But in order to do this problem, we have to know that the electric field due to a negatively charged particle points inward, as opposed to a positively charged particle that points outwards. So, knowing that, we know that the electric field to the helium still points to the right, which is this way, but now we still need something that points to the left. But this left has to point in to some negatively charged particle. So we know that the electron must be somewhere here to the left of the x. So the calculations are exactly the same as the calculations of the proton. So the electric field due to the helium is exactly the same, but we just need to calculate the electric field due to the electron at that observation location. My observation location still is 0, 0, 0, which is my origin, and that means that my helium nucleus and my electron are both on the negative x-axis. So we just plug and chugged in the formula from the port charge that I showed to you before, the 1 over 4 pi epsilon naught. Notice that the charge is negative because an electron is negatively charged. To calculate the distance of how far the electron has to be from the observation location, what we had to do is we had to again set the net electric field to be 0, which is the electric field due to the electron, plus the electric field due to the helium nucleus has to be 0, which is the same as saying that the electric field from the electron, the negative of that has to equal to the electron, the electric field due to the helium nucleus, or in other words, the magnitude of the electric field due to the electron has to be equal to the electric field of the magnitude of the electric field of the helium, but the direction is in opposite direction. So we set that equation equal to each other. Again, we just focus on the x direction because everything is in my picture is in the x direction. There is no y or z component. All that is 0. So what we're doing is we're trying to solve for g, which is the distance between the electron and the observation location. And we have, when we do solve, we get this like negative, because I didn't put the magnitude, I just put the direction of the x components of each of the vectors. But because the magnitude is always positive and the y and z component are both 0, we can just drop the negative and solve normally, because we don't want to get imaginary numbers, because there's no negative distance, there's no imaginary distance. So we have the square root, and we get that the distance between the electron and the point in the observation location is 5 times 10 to the minus 21 meters. And this is a distance where the net electric field at an x observation location would be 0. So that's all that the problem wanted us to do. Till next time, bye.